Somewhere in Shanghai, in a building with no public website, no press releases, and no name on the door that most people in the industry had ever heard, a machine was being assembled. Not a prototype. Not a laboratory demonstration designed to generate a headline and then quietly disappear. A machine intended for delivery to the most sophisticated chip factories in China. Facilities that have spent years building the most advanced semiconductors China can make, and that have been waiting for exactly this kind of tool since the day the world's only supplier of equivalent equipment was blocked from shipping it to them. The company building that machine is called Shanghai Aishengna Electronic Technology Group. It was established in 2023. It has no website. It absorbed engineering teams from at least 2 other Chinese lithography efforts and consolidated them under a single roof with 7 billion yuan in registered capital and the backing of 2 of Shanghai's largest state investment vehicles. And in the first half of 2026, it began producing the first domestically developed immersion, deep ultraviolet lithography machines China has ever put into what could be called production. 5 units in 2026. Around 20 more in 2027. Deliveries targeted at SMIC, Huahong Semiconductor, and Changxin Memory Technologies. If those names mean nothing to you, understand this. They are the companies responsible for manufacturing every advanced semiconductor China can currently produce on its own soil. And the machine being delivered to them is the machine China was banned from buying. If the story of how a country quietly builds something the world assumed it could never build is exactly the kind of thing you come here for, subscribe before we get into why this moment is simultaneously more significant and more complicated than either the optimistic or the pessimistic headlines are telling you. To understand what China has built and why it took this long, you need to understand what lithography actually is. Because most people who have heard the word have no idea what it does or why controlling it is equivalent to controlling the future of computing. Every microchip that has ever been manufactured, every processor in every phone and laptop and data center on Earth was made using a process that works roughly like photography at a scale most people cannot intuitively grasp. You start with a silicon wafer, a thin circular disc of highly purified silicon crystal. You coat it with a light-sensitive material. You shine light through a mask, a stencil of the circuit pattern you want to create. The light exposes the wafer surface and the pattern of the stencil. You wash away the unexposed parts. What remains is a layer of the circuit etched permanently into the material. You repeat this process dozens of times for different layers until a complete 3-dimensional chip has been built up from the bottom. The entire modern semiconductor industry runs on that process. And the machine that performs the critical step, the one that shines the light through the mask onto the wafer, is the lithography machine. Every single transistor in every chip you have ever used was put there by one. The reason ASML, a company based in Veldhoven in the Netherlands with a workforce of roughly 44,000 people, controls the global semiconductor industry is simple and almost unbelievable when you say it plainly. ASML is the only company on Earth that can build a lithography machine capable of printing the features required by the most advanced chips. Not the best company. The only company. Intel cannot build one. Samsung cannot build one. No Japanese or Korean or American equipment maker has succeeded in building one. ASML's most advanced machine, the extreme ultraviolet lithography system that prints features at 13.5 nanometer wavelengths, involves engineering so far beyond conventional manufacturing that the machine contains roughly 100,000 components and requires 40 freight containers, 3 cargo planes, and 20 trucks to ship a single unit from the factory to the customer. The price for one machine is over $350 million. ASML shipped around 40 of them in 2024 alone, and every chip at or below 5 nanometers in the world was made on one of them. There is no alternative supplier. There is no second source. There is no backup. Every leading-edge chip in your phone, in your laptop, in the data centers running every AI model you interact with, passed through a machine that only one company on Earth can build. That is the single most consequential industrial monopoly of the 21st century. And China was cut off from buying its products in 2019. The reason China cannot simply buy one comes down to a decision made by the Dutch government under sustained pressure from the United States. Beginning in 2019 and tightened further through 2023, which restricted ASML from exporting its UV machines to Chinese customers. Then, in additional steps that followed through 2023 and 2024, restrictions were extended to cover even some of ASML's advanced deep ultraviolet machines, the generation below UV that can produce chips around 7 to 14 nanometers using enough processing steps. China could continue buying ASML's older DUV systems, the machines it needed most, the ones that would allow it to manufacture chips at scales competitive with Taiwan and South Korea, were off the table. And critically, even the older machines already installed in Chinese factories began to face service and software update restrictions that made maintaining them at full performance progressively harder without ASML's cooperation. What China has spent the years since 2019 doing, with escalating urgency and state funding on a scale that no private company could sustain alone, is trying to build the machine it was not allowed to buy. What Shanghai Aishengna has produced is not an UV machine. Let that be absolutely clear before anything else, because the distinction matters enormously and most coverage of this development has not been precise about it. What China has produced is an immersion deep ultraviolet lithography machine. DUV uses light at a wavelength of 193 nanometers, compared to UV's 13.5 nanometers. The shorter the wavelength, the finer the features you can print. DUV cannot natively print at the scales UV reaches. It can be pushed further through a technique called multiple patterning, where you expose the same layer multiple times with slightly different masks and combine the results, effectively achieving finer resolution than a single exposure would allow. SMIC, China's largest chip maker, already uses this technique to produce chips at roughly 7 nanometers using older DUV equipment it acquired before export restrictions tightened. Multiple patterning is slower, more expensive, and more technically demanding than UV, but it works. And a domestically produced immersion DUV machine that China controls, that it can service without needing a foreign engineer's approval, and that it can improve on its own schedule regardless of what Washington or the Hague decide next, is qualitatively different from an imported machine even if the two machines have identical specifications on paper. The company that assembled this machine did not appear from nothing. It is the convergence of at least a decade of parallel efforts that China ran simultaneously, none of which fully succeeded on its own. Shanghai Microelectronics Equipment, known as SME, is the oldest player, a state-owned enterprise that has been working on lithography since the early 2000s. SME's most reliable production-grade tools in 2025 were capable of supporting processes around 90 nanometers, a generation behind what ASML was selling to Chinese customers before restrictions tightened. In late 2023, a shareholder of SME briefly announced on social media that the company had successfully developed a 28 nanometer lithography machine. The claim was retracted within days. The retraction told you something important. The gap between a working prototype and a deployable machine was wider than the announcement had implied. And the industry watchers who immediately questioned the claim understood that distinction better than the person who made it. Yangshan is a startup affiliated with SciCarrier. The equipment company linked to Huawei that has been one of the most active players in China's semiconductor equipment push since 2022. The Financial Times reported in September 2025 that SMIC was actively testing a 28-nanometer DUV system from Ultraviolet, with mass production targeted for as early as 2027. SciCarrier unveiled a suite of wafer fabrication tools at Semicon China in March 2026, including epitaxy systems, etching tools, chemical vapor deposition equipment, and atomic layer deposition machines. A demonstration that China's equipment ambitions extend well beyond lithography to the full stack of processes required to manufacture a chip. Shanghai Aishengna absorbed teams from both SMI and Ultraviolet, added capital from Shanghai Electric Holding and a subsidiary of Shanghai International Trust, and consolidated the national effort under a single entity with enough funding and talent concentration to attempt production rather than just development. Corporate and recruitment records show Aishengna and Ultraviolet share a Shanghai address. The lineage of the people inside Aishengna traces directly to every significant prior Chinese lithography effort. This was not a new start. It was a national team consolidation of everything China had learned about lithography across a decade of parallel investment. Read the significance of that consolidation carefully, because it reveals something about how China's industrial strategy has evolved. In the early years after export restrictions began tightening, China funded multiple competing efforts simultaneously, partly from genuine uncertainty about which approach would succeed, and partly because competition between programs can accelerate development when each team is learning different things. By 2023 and 2024, it had become clear that fragmented parallel efforts were generating insufficient progress against the timeline the strategic situation demanded. The consolidation into Aishengna reflects a judgment that the bottleneck was no longer ideas or approaches but concentrated execution capability, and that the best available path was to bring the best available people into one place and give them the resources to build something real rather than something promising. Now here is where the story gets significantly more complicated, and where the gap between what has been achieved and what would need to be achieved becomes the most important thing to understand. ASML's CEO Christophe Fouquet has said that China lags approximately 10 to 15 years behind in chip manufacturing, and that the actual gap may be even larger. Those numbers are not marketing designed to make a competitor seem irrelevant. They reflect a specific technical reality that is worth explaining precisely, because the headline that China has produced an immersion DUV machine could easily be read as suggesting the gap has been closed, when in fact it describes a much earlier milestone. An immersion DUV machine that can produce 28 nanometer features in a single exposure is a machine China lacked entirely in domestic production. It is also a machine that ASML was shipping to Chinese customers in volume before restrictions tightened, and that ASML now produces in far more advanced versions, representing several subsequent generations of refinement. China has not caught up to where ASML was in 2020. It has reached the capability that represents a meaningful floor for modern semiconductor production, one that matters strategically even if it does not threaten ASML's current commercial position in the slightest. The yield problem illustrates the distance remaining more clearly than any specification comparison. ASML shipped 279 DUV systems globally in 2025. 5 machines, 20 machines, 279 machines. That is the gap in production volume between China's first-generation domestic effort and the established market leader's routine annual output. But the volume gap is almost less important than the quality gap it implies. Every one of those 279 ASML machines had been refined through years of factory deployment, customer feedback, software updates, and the kind of iterative improvement that only comes from running millions of wafers through a tool in real production environments. and learning from every failure mode encountered along the way. A machine that works in a development laboratory produces one kind of proof. A machine that runs continuously in a chip factory for 12-hour shifts, 7 days a week, year after year, maintaining the kind of overlay precision and defect rate that commercial chip manufacturing requires, is a different achievement entirely. Reports from Chinese industry analysts indicated that Aishengna's machines, as of the time they began entering testing at the Shanghai Integrated Circuit Research and Development Center, had not yet demonstrated commercial-grade yield stability in the 90 to 95% range that chip factories require to make production economics work. That does not mean the machines are failures. It means they are where every first-generation production machine is, at the beginning of a learning curve that only factory deployment can ascend. Aishengna's machines will arrive at SMIC and Huahong and CXMT and begin the second phase of the test, whether they can earn the trust of engineers who need them to run reliably enough to bet production schedules on. In semiconductor manufacturing, trust in a piece of equipment is earned slowly and lost instantly. A foundry that installs a new lithography tool does not immediately run its most critical production on it. It starts with less demanding applications, monitors performance over months, validates that overlay errors stay within specification across thousands of wafers, confirms that the service team can diagnose and fix failures without extended downtime, and gradually expands the tool's role as confidence builds. That qualification process, not the delivery announcement, is the real test of whether China has built a production lithography machine or an expensive demonstration of feasibility. The UV dimension of China's lithography ambitions makes the scale of the remaining challenge even clearer, and it is worth spending time on because it illustrates why the equipment gap is so much harder to close than most coverage suggests. In December 2025, Reuters reported that a Chinese government-led project, with significant Huawei involvement, was attempting to build an UV machine using second-hand components sourced from ASML machines, parts acquired from ASML suppliers, and components from DUV manufacturers Canon and Nikon. The prototype, according to the reporting, could produce some UV light. It could not produce working chips. That gap between producing a light source and producing a machine that can pattern a wafer at production quality and commercially viable speed is measured in years of engineering development even for organizations with all the resources in the world. UV requires mirrors so flat that if one of them were scaled to the size of Germany, the highest point on its surface would be less than a millimeter tall. Those mirrors are made by Carl Zeiss in Germany, and they represent decades of accumulated expertise in optical surface finishing that does not exist in any other organization on Earth. The laser system in a UV machine vaporizes a tin droplet 50,000 times per second by hitting it 3 times with a high-powered CO2 laser, first to flatten it, then to cause the droplet to expand and thin, then to vaporize it into plasma that is approximately 40 times hotter than the surface of the sun. That plasma emits the 13.5 nanometer UV light that makes the whole process work. Because UV light is absorbed by air, by glass, and by almost every other material it encounters, the entire optical path operates in a high vacuum environment using mirrors rather than conventional lenses. Designing, manufacturing, and integrating all of those systems so that they function together reliably enough to expose millions of wafers per year without failure is a problem that ASML itself spent 20 years solving after building its first prototype. And that required the co-investment of Intel, TSMC, and Samsung in 2012 when the company was running out of money to continue funding the development. SkyCarrier has a project internally referred to as Mount Everest. The name itself tells you something about how the people working on it understand the challenge. Mount Everest does not get climbed quickly. It gets climbed with the right equipment, the right preparation, and the willingness to accept that the summit is a very long way above the base camp you are starting from. ASML's advantage is not simply a technical lead that can be measured on a specification sheet and closed with enough investment. It is a learning curve advantage that has been accumulating for 30 years through the specific mechanism of deploying machines in real chip factories and incorporating the lessons of production failures into every subsequent generation. The trend force analysis of why China cannot simply reverse engineer its way to of capability identifies this precisely. Even if a competitor copied the exterior of a lithography machine, it could not acquire Zeiss's precision optical surfaces, Cymer's laser source expertise, TSMC's testing platforms, or the decades of accumulated precision operation data that ASML incorporates into every system it ships. It is like trying to perform a symphony by reading only the sheet music. The notes are there on the page. Without the orchestra, the conductor, the hall, and decades of practice performing together, the music does not happen. And China is still in the phase of learning to read the sheet music. The global reaction to Aishengna's announcement was itself instructive about how the industry interpreted the news. ASML's share price fell sharply when the first reports of Chinese DUV production broke, briefly erasing tens of billions of euros in market value before partially recovering as more precise reporting about the machine's actual capabilities and production volumes emerged. Investors' initial reaction, pricing in a significantly larger competitive threat than the subsequent analysis supported, reflected a fear that has been building in the semiconductor equipment industry for years. Not that China will match ASML tomorrow, but that China has demonstrated it can make progress on a problem the industry had assumed was essentially unsolvable in any relevant time frame. That fear is not irrational. The electric vehicle story, the battery story, the solar panel story all followed the same arc of initial dismissal, followed by unexpectedly rapid scaling once China committed national industrial resources to a specific technology challenge. The semiconductor equipment community is watching Aishengna and asking whether this is the beginning of that arc. And the honest answer is that it is too early to know. What China has demonstrably built, separate from the question of how quickly the technical gaps will close, is a new kind of institutional infrastructure for this specific engineering challenge. AME's technology, the spin-off from SME that is focused on commercializing packaging and back-end lithography tools, shipped its 500th stepper lithography machine in August 2025 and claims approximately 90% of China's domestic market in its equipment category. That category, back-end and packaging lithography at less advanced nodes, is less strategically significant than the Immersion DUV systems Aishengna is producing for leading-edge manufacturing. But the 500th machine knows things the first machine did not, and the engineers who designed, delivered, installed, commissioned, and serviced those 500 machines have accumulated expertise that no amount of laboratory research generates. China's lithography supply chain, from optical components to precision stages to control software, has been building out in the categories where export restrictions left room for domestic development, and the expertise accumulated in those categories is not irrelevant to the harder challenges further up the technical stack. The 42% of ASML's third quarter 2025 revenue that came from China, for the older DUV tools that remain permitted for export, is another piece of context that the export restriction story tends to obscure. China was, as of late 2025, still ASML's largest single customer by revenue. Chinese chip manufacturers continued buying every ASML machine they were legally permitted to purchase, in volume, because the performance gap between those older ASML tools and anything domestically available was real and consequential for production. The ban applied to the newest and most capable systems. For the systems Chinese companies could still buy, They continued to prefer ASML's proven tools over domestic alternatives wherever that choice remained available. That preference is itself a signal. The domestic options exist in some categories. Chinese engineers with an actual production choice between an ASML tool and a domestic equivalent have generally chosen the ASML tool. Changing that preference requires domestic tools that match ASML's performance in the categories where choice exists, and that match has not yet been demonstrated at the level that would cause production engineers to voluntarily switch. The Ministry of Science and Technology's 110 million yuan contract award to SME for a step and scan lithography system in late 2025 is representative of how the domestic market is being structured to support the development of these capabilities. State procurement is not the same as commercial adoption. A government ministry buying a SME machine for state-funded research is creating revenue for the company and an opportunity to run the machine in a real facility, generating the operational data that development labs cannot provide. It is not the same as a private sector chip manufacturer choosing a SME tool over an ASML tool because the SME tool delivers better economics. Building the bridge from state-directed development adoption to genuine commercial competitiveness is the next phase of the challenge, and it is one that China's other technology industries have successfully navigated. The path from government-backed development customer to commercial market winner in EVs and solar panels required years of scaling, cost reduction, and performance improvement funded partly by captive domestic demand. The lithography trajectory appears to be deliberately following the same model. Step back now from the specific technical details and look at what the overall picture actually shows. China in 2026 has domestic lithography production at immersion DUV scale, at small volumes, with real technical gaps relative to the equipment it cannot buy, entering customer qualification at its most advanced chip makers. China has prototype UV efforts at a stage where producing light is demonstrated, but producing chips is not. China has a growing ecosystem of semiconductor equipment companies across categories adjacent to lithography, accumulating production experience and customer feedback at a pace that did not exist 5 years ago. And China has committed institutional resources, state capital, consolidated talent, and strategic urgency to this specific technology challenge in a way that has no clear precedent in the semiconductor equipment industry's history. None of that means the gap will close on the timeline that the most optimistic coverage suggests. The specific technical challenges of HUVE are not straightforwardly analogous to the challenges China faced in batteries or solar panels, where the physics were understood and the problem was manufacturing economics. UV involves physics at the edge of what is currently achievable, implemented in an integrated system of over 100,000 components that took the world's best optical engineers 30 years to perfect working together. The organizations that hold the key expertise in optics, laser systems, and precision mechanics that UV requires are in Germany, the United States, Japan, and the Netherlands, and their export to China is itself restricted. China is attempting to build the orchestra while someone else controls access to the instruments. What has changed is the assumption that the gap was effectively permanent. That assumption has been replaced by something more uncertain and more honest. The gap is large. The challenges are genuinely hard. China has demonstrated it can make real progress on problems that seemed intractable. And nobody outside of a handful of engineers inside Aishengna and SMIC knows exactly what the next 5 years of production deployment will reveal about how quickly the learning curve actually moves when the machines are running real wafers in real factories rather than development prototypes in government research centers. That uncertainty, more than any specific technical milestone, is what the Aishengna announcement actually introduced into the semiconductor equipment landscape. If this story gave you a clearer picture of something that most coverage has reduced either to a triumph or a footnote, subscribe and turn on notifications, because the semiconductor equipment race is the foundation underneath every other technology competition that matters over the next decade. Here is the question worth leaving with. Is China's lithography push the beginning of the same industrial catch-up story it executed in electric vehicles and solar panels, where initial dismissal was followed by unexpectedly rapid scaling? Or is semiconductor equipment genuinely different in kind, so dependent on accumulated ecosystem knowledge and global supplier networks that no amount of state capital and engineering talent can compress the timeline in the same way? Both arguments have serious technical weight behind them. Drop your answer in the comments, because this one is genuinely not settled yet.